Alright, in this video we study a new kind of multiplication between two vectors that is called vector product, or also known as cross product. Unlike the scalar product, where the result of the scalar product is a scalar, the result of the vector product is a vector. So let's start. We have already studied the scalar product. So let's say we have two vectors, A and B, in the n-dimensional vector space. Then the result of the scalar product, let's write it like this, is a real number or a scalar. Okay, but unlike this scalar product, we can define another type of multiplication that is called a cross product, written like this. And this is an element of the n-dimensional vector space, but this n must be equal to 3. Okay, so that means both A and B must be three-dimensional vector, and the result of the vector product is again a three-dimensional vector. So this special multiplication vector product is defined only for three-dimensional vectors, and you should be wondering, why can't we define a similar multiplication for other dimensions? Maybe you should try to define some similar type of multiplication, but it's not so easy. Well, anyway, we just stick to three-dimensional spaces in this lecture. So here's the definition of the vector product. Let A and B be three-dimensional vectors. And let's say their components are as follows: A1, A2, A3. So we consider row vectors here, B1, B2, B3. And the vector product, which we write A cross B, so because of this we also call it a cross product, is yet another three-dimensional vector that has the following components, that are A2, B3 minus A3, B2, and A3, B1 minus A1, B3, and A1, B2 minus A2, B1. So this looks a little bit complicated, but we will see the pattern later. So anyway, for these two vectors, the cross product is defined by this, so by these components. And sometimes, instead of writing like this, A cross B, some people might write like A, B, enclosed in square brackets. Now, let's look at these components more closely. So the first component, A2, B3 minus A3, B2, is also expressed as a matrix determinant of this 2 by 2 matrix. That is A2, A3, B2, B3, right? So A2 times B3, that's this, minus A3 times B2, that's this. And similarly, the second component, A3, B1 minus A1, B3, can be written as a matrix determinant. Okay, so in this case, A3, A1, and B3, B1. And also the third component, A1, B2 minus A2, B1, can be written as this matrix determinant, A1, A2, and B1 and B2. So although these components look complicated, if we express in terms of matrix determinants, you can see some patterns. For the first component, we just remove the first components of vectors A and B and just align the second and the third components of each vector. So A2, A3, and B2, B3. Then calculate the determinant made of this matrix. And for the second component, we remove the second components of A and B, and we swap. Or maybe, using the property of matrix determinant, maybe you can write like this, negative sign, and swap these columns, and A1, A3, B1, B3, same thing. So the second components are removed, and we make this 2 by 2 matrix determinant and calculate the determinant and mind the sign here. And for the third component, we remove the third components of A and B, and we align the elements A1, A2, B1, B2 in this way, then calculate the determinant. And those are the components of the vector product. And what about the sign? So the first component has positive sign, and the second component has a negative sign, and the third component has a positive sign. So this looks like, again, a matrix determinant, right? So if we want to calculate matrix determinant of 3 by 3 matrix, let's see. So A1, A2, A3, and B1, B2, B3. And let's say we have other components. Okay, if we want to calculate the determinant of this matrix, then let's expand along the first row. Then we have so negative 1 to the power of 1 plus 1, so 1 element here, and E1, and we have this determinant. And for the second component, this one, negative 1 and 1, 2 element, and E2, and this, so A1, A3, B1, B3. And for the third component, 1 plus 3 and E3. And this smaller matrix is here, A1, A2, B1, B2. So this becomes the first component, and this times this, so that's negative sign here. So this becomes negative 1, and this becomes positive 1, and this is positive 1. So this sign times this thing is the second component, and this sign times this thing is the third component. Okay, now let's see some basic properties of the vector product. Okay, so here's a theorem. And we assume A and B are three-dimensional vectors, real vectors, three-dimensional. And then we have the following properties. 1, if A is a zero vector or B is a zero vector, then A cross B is a zero vector. And second, if A and B are parallel, A and B are parallel to each other, so that means there exists some lambda, which is a real number, such that A is lambda times B, or there exists some another real number such that B is equal to mu A. So in this case, we say A and B are parallel, right? So if this is the this is the case, then we have the cross product of them being 0 vector. And third, A cross B, if we swap the order, then the result is negative of B cross A. So that means cross product is not commutative. Okay, and for any real number lambda, we have lambda times A cross B is equal to lambda A cross B, or this is also equal to A cross lambda B. And 5, let's say let's define unit vectors E1 as 1, 0, 0, and okay, let E1 be this, E2 be 0, 1, 0, and E3 be 0, 0, 1. Then we have E1 times E2 equals to E3. And E2 times E1 equals to, wait a minute, E2 times E3 equals to E1. And E3 times E1 becomes E2. Okay, so this is like circular. Okay, so 2, 1, 2 becomes 3, and 2, 3 becomes 1, and 3, 1 becomes 2. Okay, so 1, 2, 3, 2, 3, 1, 3, 1, 2. So it's like 1, 2, 3. It's like rotating. Okay, so 1, 2 gives 3, and 3, 2, 3, 1 gives 2, and 2, 3 gives 1, and so on. So these are the basic properties of cross product or vector product. So I don't give the proof of all of them, but you should try to prove all of them. Okay. So for example, this is easy. Just apply the definition to 0 vector. So for example, the first element, if A1 is A is 0, 0, 0, if it's a 0 vector, whatever the vector B is, we have the first element A2, A3, B2, B3 is 0, 0, B2, B3. This determinant is, of course, 0. And you can show the same thing for the second and third component, and all of them becomes 0. And for the second part, if A is proportional to B, so if A and B are parallel, then the elements of A can be expressed as lambda B1 and lambda B2 and lambda B3, right? So the first component of A cross B, so the first component becomes this lambda B2, lambda B3, and B2 and B3. But this is determinant, right? So just use all the properties of determinants. So first we can get this lambda out, and that's B2 and B3 and B2 and B3. Now we have two rows that are identical. So in that case, the determinant is 0. And you can show the same thing for the second and third component, and so on, and try all the others. Next, we would like to combine the scalar product and the vector product. For this video, we denote the scalar product by dot. Okay, that means, so previous videos we wrote scalar product like this, but this is also denoted as A dot B. Okay, they mean the same thing. Okay, now using this notation, let us define the triple product. So let's say we have three vectors, A, B, C, that are three-dimensional vectors. Then the triple product of these three vectors is defined as this: A dot B cross C. Okay, so make sure that you understand the strength of connection of between operators. Okay, first we calculate this vector product. Then between this vector and this vector, we calculate the scalar product. Okay, so the result is a real number. Okay. Because otherwise, it doesn't make sense, right? Because if we mean this, then the result of this scalar product is a scalar. But this is still a three-dimensional vector. We cannot define the cross product between, or the vector product between a scalar and a three-dimensional vector. So this doesn't make sense. So if we just write without parentheses, we mean this. Okay, now here's a important property of the triple product. Let's say we have A that has components of A1, A2, A3, and B, B1, B2, B3, and C, C1, C2, C3. Then the triple product between these, among these three vectors is given by the determinant A1, A2, A3, B1, B2, B3, C1, C2, C3. So let's show this. Actually, this is not so difficult. So A dot B cross C. And okay, so first consider the dot product. Okay, so A1 times B cross C, the first component of B cross C, and A2 times the second component of B cross C, and A3 times the third component of B cross C. Okay, and just apply the definitions here. And as we have learned, the first component of B cross C is the determinant, B2, B3, C2, C3. And the second component is again a determinant with, let's put negative sign here. And what was it? That should be B1, B3, and C1 and C3. And the third component is yet another determinant. That is B1, B2, C1, C2. Now look at this expression. Now this is actually the determinant of the 3 by 3 matrix. So that is equal to this one. So right hand side. And we are done. And as a corollary to this theorem, we have the following result. So A dot B cross C is equal to B dot C cross A is equal to C dot A cross C dot A cross B. Yeah. So do you see why? For example, let's consider this part. Okay. So we have seen that this is equal to the determinant. So let's write in the form of column vector of row vectors. Okay. So this is the determinant, this. Okay. Now, this is equal to, if we swap once, okay, let's swap the first row and the third row, then we have negative sign here. So C, B, A. Now let's swap the first row and the second row. Then we have another negative sign, so that will cancel this negative sign. So we have B, C, A. But this is equal to this. So we just proved this part. And similarly, you can prove this part. And yet another easily derived corollary of this theorem is that the dot product A between A and A cross B, so whatever the B is, this is equal to 0. It's not vector, it's a scalar, so it's a real number 0. So you should prove this. It's actually easy if you use the property of determinants like this. And of course, so this A and this A are the same, but we also have this B dot A cross B is also 0. So what these equalities mean is that the vector A is perpendicular to the cross product involving A and something, okay? And also B is perpendicular to this cross product. So in 3 dimensions, let's say we have A and B. And B, and we will actually later prove that the cross product of these 2 vectors is perpendicular. We have just actually proved it to this vector. So the cross product will be something like this. So this cross product is perpendicular to both A and B. Okay, and the direction we haven't determined yet, but usually, not usually, but it will be clear that the direction of the cross product will be like this. It's called the right screw rule. So first vector here, so the first vector is A in this case, and the second vector is B. So first put this and rotate this A to the direction of vector B. Then the direction where the usual right-handed screw will proceed is the direction of the cross product. Okay, so using your right hand, first point your pointing finger to this direction and move your middle finger to this direction, and now your thumb is pointing this direction, pointing to the direction of the cross product. So right-handed rule. And also, we have a distributive law for cross product. So A times B plus C is equal to A cross B plus A cross C. So you should try to prove this. You can just directly calculate both sides and compare them and see they are indeed equal. Or maybe you can use some properties of matrix determinants. Either way is fine. Okay, now let's try to characterize the meaning of vector products. First thing we show is this. Of course, we assume A and B are 3-dimensional vectors. And if A dot B, so the scalar product is 0, then the norm of the vector product is the product of the norms of the 2 vectors. Okay, remember what the norm is? It's basically the length of the vector. Okay, so if A is A1, A2, and A3, then the norm of A is the square root of A1 squared plus A2 squared plus A3 squared. So in three-dimensional space, let's say if we have 1, 2, 3 x, y, z coordinate, let's say x1, x2, x3 coordinate, and we have a vector. Here is A1, A2, A3. So this length is the norm of the vector. So actually, this is straightforward by direct calculation to show this lemma. But it can be quite complicated and tedious. So we need some trick. Okay, so first, what does this mean? So this means A1, B1 plus A2, B2 plus A3, B3 is equal to 0. So this means the scalar product is 0. So let's square both sides. Then we have, so square this. We have A1 squared, B1 squared, A2 squared, B2 squared, A3 squared, B3 squared. Oh, so it's not 3, it's 2. And 2 A1, B1, A2, B2, plus 2 A2, B2, A3, B3, plus 2 A3, B3, A1, B1 equals to 0. So from this equation, we have, let's see. Okay, this is equal to negative of this and this and this. Okay, so A1, B1 squared plus A2, B2 squared plus A3, B3 squared is equal to negative 2 of this and this and this. Now, let's calculate the norm. For the sake of simplicity, we calculate the norm squared instead of norm. So in that way, we can get rid of this square root. Okay, so A cross B norm squared is, so the first component is, what was it? A2 B3 minus A3 B2 squared. So this is the first component squared. And the second component is A3 B1 minus A1 B3 squared. And the third component is, what was it? A1 B2 minus A2 B1 squared. So let's expand everything here. And let's see. From here, we have A2 squared B3 squared plus A3 squared B2 squared minus 2. Let's see, A2 B3 A3 B2. And from this one, A3 squared B1 squared A1 squared B3 squared minus 2 A3 B1 A1 B3. And from the third component, A1 B2, so both squared, A2 B1 squared, 2 A1 B2 A2 B1. Okay, now let's look at this part. Okay, so we have negative 2, negative 2, negative 2, and A2, B2, A3, B3, right? So here we have, let's see, A2, B2, A3, B3. So this term is equal to this term. And we have, let's say, A1, A3, B1, B3. And we have A1, B3, and A3, B1. So that's this term. And this term is again so A1, B2, A2, B1, A1, B2, so B1, B2, so this term. So this, all these thing is equal to all of these thing. So we can replace this with the left-hand side of this equation. So that is, so let's leave this A2, okay. Can we just copy and paste? Okay, nice. And paste. Okay, so this thing plus A1 B1 squared plus A2 B2 squared plus A3 B3 squared. Right? So A1 B1, A2 B2, A3 B2, B3. Okay. So now let's simplify this. Okay, so how can we simplify this? We want to factorize somehow, and let's focus on A1 squared here. So A1 squared is also here, and also here. So A1 squared is involved with B1 squared, and B2 squared, and B3 squared. Next, consider A2 squared here. So A2 squared is here, and where else? Here. Okay. So A2 squared is involved in B1 squared, B2 squared, and B3 squared. And finally, consider A3 squared. So A3 squared is here and here, and B1, B2, B3 all squared. So we have the same factor here. So again, we can factorize to have A1 squared plus A2 squared plus A3 squared times B1 squared, B2 squared, B3 squared. But this is the norm A squared, and this is norm B squared. Thus, we have the claim that this holds. These tedious calculations, we get this result, but what does that mean exactly? So this means if A and B are perpendicular to each other. By the way, why is this perpendicular? Remember? So if the angle between two vectors is theta, then A dot B, so the scalar product between A and B is given by this, A norm and B norm and cosine theta. Remember? This is the result we have got when we study the scalar product. So if this is equal to 0, and if A and B are non-zero vectors, okay, then the only possibility is that cosine theta is 0. So that means this angle here is the right angle. So it means this. So this is A and this is B. Okay. So theta is something like pi half or maybe negative pi half, or some periodic analog of these two values. So anyway, if A and B are perpendicular to each other, or we also call it orthogonal to each other, orthogonal to each other, then the length of the cross product, A cross B, is the product of the norms of A and B. Okay? So this holds if these two vectors A and B are orthogonal or perpendicular to each other. So the natural question now is, what if A and B are not perpendicular to each other? So if A and B are parallel to each other, we already show that the cross product is a zero vector. So that means the length of the cross product between two parallel vectors is zero. Okay, so if A and B are something like this, A and B are parallel to each other, then the length of the cross product is just zero. Okay, then what happens in between? So here's the theorem. So if the angle, okay, let theta be the angle between A and B, then the length or the norm of the cross product between A and B is this: A norm times B norm times the absolute value of sine theta. Okay, so compare this with the cross product, the scalar product. So A dot B is this, cosine theta. Okay, it's similar, but different. Okay, first of all, because the result of the cross product is a vector, so we need to take the norm here. And in case of scalar product, the result is of course scalar, so we don't have to take the norm. But of course, if we want to, we can take the norm, which is just the absolute value of a real number. But anyway, so on one hand, we have cosine theta for the scalar product. On the other hand, we have sine theta for the vector product. Okay, so let's prove this. We first start from here. Okay, and then we define a unit vector A hat by this: 1 over norm of A times A. Okay, so that means if we have a vector A, then A hat is something like this. A hat is this. The length is 1. Okay, and using this, we define a projection of vector B, which means this: B parallel is defined by A hat dot B and times A hat. Okay, and B perpendicular is defined as B minus B parallel. Okay, so let's consider the meaning of this one. So we have the vector A here and the unit vector A hat. And let's say we have a vector B. Then A hat dot B is the scalar product between A hat and B. Okay, and the length of this is, so A hat dot B is, so the length of A hat is 1 because it's a unit vector. So this becomes B norm times cosine theta. So theta is the angle between A and B. Okay, so this is this. Okay, and so this B parallel means it's in the direction of A hat, but it's scaled by this much. So by this much, we mean this. So the length of this vector B is B norm, of course. And cosine theta is then cosine theta times this length is this length. So B norm and cosine theta. Okay, let's change the color. So this is B parallel. Okay, so the length, this length, so this is the right angle actually. So right angle here. So we project vector B onto vector A. And that vector is defined to be B parallel. Okay. So this unit vector A hat is scaled by this much, and that is B parallel. Okay. Then we define B perpendicular, this one, by subtracting B parallel from the original B. So what this means is this. So we have vector B here, and we subtract B parallel. So that means we revert the direction of B parallel. So we move this way. So the result is this vector. Okay. So this vector from here to here is B perpendicular. So that means this is the perpendicular vector, a vector perpendicular to A. Okay, we'll see this. So what we just did is, from here, we can rewrite B as the sum of B parallel plus B perpendicular. So B parallel is the parallel component of B. Parallel means parallel to A. Okay, and B perpendicular means the component of B that is perpendicular to A. So any vector can be split into these two components, given yet another vector, in this case A vector. And it's obvious that B parallel is parallel to A, and let's see if B perpendicular is indeed perpendicular to A. So consider this dot product. B perpendicular time dot, let's see, A hat. Okay, and B perpendicular is B minus B parallel, and dot A hat, and B, so dot product is distributive, so we can expand this like this, and B parallel dot A hat. And now the definition of B parallel is this one. So let's consider that B dot A hat and B dot A hat and A hat. A hat dot A hat. Okay, so this part corresponds to this. Okay, maybe I shouldn't put hat here. Okay. So this is a vector and this is a vector, and we are taking the dot product here. So we have B dot A hat, and A hat dot A hat is 1. So it's just 1. So we have B dot A hat minus B dot A hat, so that is 0. So that means these two vectors, B perpendicular and A hat, are perpendicular to each other. So this is, okay, this is B parallel and this is B perpendicular. So we have this triangle with a right angle here. Okay, so using the Pythagorean theorem, we have the length of vector B squared is equal to the sum of the square of the other edges. So B parallel squared plus B perpendicular squared. So this comes from Pythagorean theorem. Okay, from this equation we can calculate the length of B perpendicular. Okay, so this thing is equal to b squared minus b parallel squared. Okay, now this b is b, and this thing, let's see, we have, where is it? Okay, so the length of b parallel is this. That is b squared and cosine theta squared. Right? That's how we defined b parallel. So this is b norm squared, so 1 minus cosine squared. That is sine squared. Okay. So from this, we have b perpendicular squared is b, no, not squared, let's see. The norm of b perpendicular is the norm of b times the absolute value of sine theta. Okay, now we are getting closer. Now, A cross B, consider this, is A cross, so B here is split into two parts, parallel and perpendicular, right? And A cross, so we can distribute this. So this is A cross B parallel plus A cross B perpendicular. However, B parallel and A are parallel to each other, so the cross product becomes 0. So this is 0 vector, and we have this. Okay. Of course, 0 vector has 0, doesn't affect by addition, so we have this. So this is actually equal to this. Therefore, and we have already seen that A and B perpendicular, they are perpendicular to each other. So the norm of A cross B is equal to the norm of A cross B perpendicular. But this is equal to, since these two vectors are perpendicular to each other, this is just the product of the norms of A and B perpendicular. But the norm of B perpendicular is this, so this is equal to A and B and sine theta. And we are done. Okay, now let's consider the geometric meaning of this relation. Okay, so if we have two vectors in three-dimensional space, A and B, okay, these two vectors can define a parallelogram. So it's a parallelogram. And suppose the angle between A and B is theta, then what is the area of this parallelogram? It's actually this. Okay, so this length times this length times sine theta. So sine theta is actually this height, right? I mean this B, the length of B times sine theta. So maybe we should take the absolute value here, is this height of this parallelogram. Therefore, this is actually the area of this shape. So the geometric meaning of the vector product is this. If we have A and B, then the direction of A cross B is perpendicular to both A and B, and the length corresponds to the area of the parallelogram made by A and B. And of course, there is still a problem of direction. Although A cross B is known to be perpendicular to both A and B. It can be either this direction or maybe that direction. So which one is correct? So this direction is determined by the direction of the angle, okay? So if we calculate A cross B, so A first and B next, in that case, we measure the angle between A and B from A to B, okay? So in this direction. So if A is here, B is here, so the angle is measured in this direction, okay? First A, then B. So first we point with our right hand, point this direction, so pointing finger in this direction, and move this finger to this direction. Then the direction where the thumb is pointing to will be the direction of A cross B. Okay, so if the angle is switched, is negative or positive, it depends on how you see the space. But so if we swap the order of A and B, then this is equal to negative B cross A, right? So in that case, B first, A next. So B first, A next, but we have negative sign here, so we still have the same direction. Okay, finally, let's consider the geometric meaning of the triple product A dot B cross C. Okay, now we have three vectors. Say A and B and C. Okay, first consider B cross C, and we know that the result is a vector that is perpendicular to both B and C. And so perpendicular to B and perpendicular to C. And the length of that vector is equal to the area of this parallelogram. Now, if we add one more vector A, then these three vectors A, B, and C defines a solid shape called parallelepiped. Something like this. Okay. Okay. So this edge is parallel to this and this and this. And this edge is parallel to this and this and this, and this edge is parallel to this and this and this. So this defines a parallelepiped. Let's write it. Parallelepiped. I hope this spelling is right. Let's see. Parallelepiped. Okay. It's really hard. Anyway, and then let's define a unit vector along B cross C. Let's call it U. So U can be, for example, defined as this. Okay. Then consider the dot product, A dot U. Okay, so that is equal to this length. Okay, so let's say the angle between A and B cross C is phi, then this is equal to A norm cosine phi, because U is a unit vector, so its length is 1. So this length is the dot product. Okay. Now, A dot B cross C. So B cross C can be expressed as A dot U and 1 over, wait a minute, times B cross C norm. So B cross C can be expressed as U times this norm, right? So this thing. And so this part is this. So A norm and cosine phi and B cross C. So B cross C, its norm is the area here, right? And A norm times cosine phi is the height of this parallelogram. So that means this area times height is the volume of the parallelepiped made of ABC. Parallelepiped made of ABC. So this and was actually the determinant. So this determinant means this triple product, and this triple product has this geometric meaning of this volume of this shape. And it's not just the volume, but it's a signed volume. Okay, signed means it can be negative as well as positive. So positive is okay. So the positive case happens when the angle between A and B cross C is less than the right angle, so pi half. If it is greater than pi half, then that means, for example, if A instead of in this direction, if A is pointing in this direction, that means the angle is greater than pi half. In that case, the volume becomes negative, so it's signed volume. It can be negative. So the sign represents the relative orientation between this cross product between B and C and A. So if they are more like pointing to more or less the same direction, then it's positive. If they are more or less pointing to opposite direction, that means the angle between them is greater than pi half, then it's negative. Okay, so that's the geometric meaning of the triple product. And I think that's all for this video, and see you later.